It's time for some tea. 1.4 billion years ago, two black holes merged into one, releasing a tremendous amount of energy in the form of gravitational waves. 1.4 billion years later, they reached the Earth, and these waves were picked up by two L-shaped tunnels in the US on the 14th of September 2015. They registered as a chirp lasting for less than a quarter of a second and was given the name GW 150914. After 5 months of checking, cross-checking, and intensive data analysis, the LIGO collaboration announced their discovery to the world. A year later, the LIGO collaboration's leaders won the Nobel Prize. More importantly, the discovery of gravitational waves opened up a brand new frontier of astronomy, making it one of the most exciting discoveries of the 21st century. Watching this, you might be thinking, wow, ain't science fantastic? But science involves the scientific method, and part of the scientific method is to be skeptical of every single aspect of your observation. Generally, when a capital B big discovery happens in science, specifically in physics because that's the field I'm most intimately aware of, there are two camps. One that's super excited and starts looking into the future, and another that's skeptical and tries to find everything wrong with it. Both of these camps are important and necessary because one pushes the frontiers of the field and the other strengthens the foundations of the field. And so today I want to tell you a story. That time when some people thought that LIGO actually didn't see anything, or rather anything interesting. A story that involves humans, two different scientific institutions, catfighting across continents and academic journals, Sabine Hossenfelder, and some actual corrections, and finally, how it all shook out in the end for LIGO and the future of gravitational wave astronomy. To begin, we need to go all the way back to that fateful day in 2015. To understand the drama, we first need to look at LIGO. LIGO observes gravitational waves using laser interferometers. These interferometers are the two L-shaped tunnels in the United States, about 3,000 kilometers apart. These tunnels have a laser running up and down and later recombine or interfere. Since gravitational waves stretch and squeeze space, measuring how much they interfere allows us to reconstruct what the wave passing through looked like, or sounds like. There's a lot of engineering and scientific details I'm skipping here. I've included some in the description if you're interested, but basically, it was quite a feat. However, there were three suspicious things. Thing number one, LIGO had no alibi because it was the only observatory that detected the signal at all. There was only one other observatory on the planet that could have detected it, but that one was offline. But LIGO isn't one detector, it's two. Because they're quite far away, any sources of noise will be isolated to just one of the detectors. The gravitational wave signal was big and was picked up on both detectors with a time delay that was well constrained by the speed of light, which is the speed at which these waves travel. The reason why LIGO is two detectors is complicated, and we'll get to that later. Thing number two, LIGO wasn't actually set up to properly detect gravitational waves when it detected the gravitational wave. Because these machines are extremely sensitive and highly complex, it often has two separate operating modes, an engineering mode and a science mode. An engineering mode is when the machine is operating in a completely predictable way, to just check if all systems are nominal. This comes with the trade-off of maybe not being very sensitive or not very precise or whatever. Additionally, part of a science run is to alert all other astronomical stations around the world once an event was detected. This is because gravitational waves are produced by some of the most violent events in the universe. And so, if LIGO picks something up, then other telescopes looking for bright flashes in the sky might as well. But they didn't because LIGO didn't alert them. And thing number 3, the signal they recorded was in the frequency range to which the observatory happened to be the most sensitive. Which is just hella suspicious. Let me explain how buck wild this is with an example. Say you have a fancy microphone that is sensitive to certain frequencies but not others, and you're trying to prove that a certain bird exists in a dark forest by recording its bird call. The moment you turn the microphone on just to see if everything is working, not only does it pick up the bird call, you are the only person who heard it because the other person was asleep, but it's also right smack in the sweet spot of where your microphone is most sensitive. And that is why it took them nearly 5 months to verify and cross-verify that even though all of these things seem suspicious, it was quite literally a happy coincidence. The paper was published on the 11th of February in 2016. 8 months later, however, there were some seeds planted in the world of gravitational wave astronomy. On the 10th of October 2016, Hao Liu and Andrew Jackson published a paper titled Possible Associated Signal with GW 150914 in the LIGO data. Okay, here's how LIGO actually detects a signal. Each detector on its own isn't sensitive enough to fully see the signal. Rather, what happens is you take data from both the detectors and then try to match parts of the signal that's present in both detectors. Since random noise should be pretty isolated between the two, the noise gets suppressed and the actual gravitational wave signal gets enhanced. It's a lot of complicated math. This paper presents a different method that tries to achieve the same thing. But in doing so, they found another signal that wasn't the main signal, but with the exact same time delay. This signal started from 10 minutes before the big GW 150914 and lasts for about 45 minutes. Okay, I'm just going to call it Gwen. I can't be bothered to say these numbers over and over again. I have a lot of thoughts on how astronomers name things, but that's a video for another day. Now, they were trying to not stir up too much drama here and claim that, okay, the signal is pretty weak and it's possibly not coming from some instrument error that's trying to measure the thing that you actually want to measure. But it didn't end there, because 8 months later, Jackson, Liu, along with the other physicists in the Bohr Institute in Copenhagen, published the sequel on the time lags of the LIGO signals, where they go back to that highly correlated noise in both detectors. For context, the 2016 paper, the first one, concludes that anything correlated between the two detectors cannot be noise, obviously, and so has to come from something astronomical, but it doesn't quite look like a gravitational wave either. It's complicated, it's messy, it #needs further research. On the other hand, the 2017 paper claims that there are specific components of noise that seem to be highly correlated between the two detectors, which has nothing to do with gravitational waves at all. To take things further, they have to originate from the instruments because the detectors are basically identical, and that the signal these instruments might have caused would look very similar shape-wise to the big Gwen signal. Now, this is less shit-stirring and more muddying the water. By saying that there were components that can resemble the Gwen signal that doesn't originate from some astronomical source, it casts doubt on the actual Gwen signal. Think about it. If you ignore the story I told you in the beginning, and all you got was this signal, what are the odds that this signal actually corresponds to the merging of two black holes? According to the 2017 paper, the odds are lower than what the original announcement claims. In scientific parlance, it decreases the statistical significance of the Gwen signal. This paper was published in the archive, which is a preprint, or the purgatory where physics papers go before they get published in a journal proper. This means that not a lot of people, even within the physics community, knew about this. Until I have a lot of thoughts about Sabine Hossenfelder. I won't share them here explicitly. On the 16th of June, 3 days after the Copenhagen team published their paper, famed internet physics provocateur Sabine Hossenfelder wrote an article for Forbes. You know, that magazine you strongly associate with physics and nuanced takes. I should also point out that Sabine Hossenfelder is a theoretical physicist, although not one specializing in gravitational waves or the analysis of gravitational waves. And that's fine. I'm not specializing in gravitational waves either, and look at me shooting my mouth off. In this article, Hossenfelder basically covers what I just did, editorializing here and there about big physics. However, she does reveal something very interesting about the Copenhagen team's relationship with LIGO. Quote, "Upon my inquiry with a member of the LIGO collaboration what to make of the paper, I got the annoyed reply that the collaboration's management recommends to respectfully respond that we have talked at some length with the group in the past and do not agree on the methods being used and thus with the conclusions. Another let me know that a response is not planned." So it's no longer some fringe archive paper, it's now in the mainstream, and people are talking about it. 2 days after the Forbes article, Ian Harry, a postdoc at the Max Planck Institute, wrote a blog post which consists entirely of rebutting the Copenhagen claim. To summarize what the blog post said, basically, the Copenhagen team had missed out on some subtleties in their data analysis, and upon performing the same analysis as outlined in the paper, he did not find the spurious signals that they claimed to have found. Very quickly, however, the Copenhagen team responded on their website that Harry's code had flaws and their argument stands, to which Harry responded that the flaw was a typo that he had already fixed before the team had responded, and that either way, it doesn't actually affect the actual analysis. Now, what these subtleties were are probably a bit beyond the scope of this video. You can check out the blog post below yourself, below the like button, along with all of the other papers and blog posts involved during this entire battle. But basically, once this happened, Andrew Jackson, the head of the Copenhagen team, was getting increasingly... Soon after that, by the end of the month, we get Quanta magazine weighing in on the issue. Jackson refused to be interviewed for this article, along with the rest of the members of the Copenhagen team, claiming in an email correspondence, "Public polemics tend to harden positions and do not advance the desired end." And just to remind you, LIGO had detected 2 more gravitational waves by this point, and the Copenhagen team said nothing about it. But wait, did LIGO win a Nobel Prize without clarifying these things first? The world apparently kept spinning, because while this tiff was going on, it was getting increasingly clear that LIGO was winning the Nobel Prize. And they did, in October of 2017. Now, I don't know if this drama had any bearing on the decision, but then the Nobel Prize is famous for awarding people things without really waiting much for proper verification. I have a lot of things about the Nobel Prize. In any case, they won the Nobel Prize and everything goes quiet for a bit. There's nothing from the Copenhagen team, and LIGO kept detecting more gravitational waves. The only real controversy in this time that I like to touch upon was how the Nobel Prize was actually awarded. The rules of the prize dictate that a maximum of 3 alive scientists would be awarded, which not only ignores the work undergone by thousands of physicists and engineers in the LIGO collaboration, but also the work of a key experimentalist who died in 2016, well after the Gwen announcement. Why didn't the Nobel Prize award them in 2016? That's a video for another time! Apart from that, all was basically quiet on the front of the Gwen signal. Until... It takes basically almost another year before there's any progress in this entire story. The reason why the Copenhagen team had any support at all was that they were totally independent of LIGO and big physics. And generally, independent studies take time because they don't have access to the full raw data and the same resources that LIGO does. We get a publication from Green and Moffat of the Perimeter Institute on the 10th of September 2018. This paper considers a variety of techniques to find the signal to confirm the original detection, and quote retweets the Copenhagen team's 2017 paper saying that they just did the analysis wrong because of the nuances of working with frequency spectra. A couple of months later, Nielsen and friends used the same statistical analysis that the Copenhagen team used to find that basically no significant spuriously correlated signal was found, in that just with a tiny tweaking of the parameters, the spurious signal either appears or disappears, meaning their method is not very robust, meaning the method is not good. Now remember, all of this is for Gwen, the first ever gravitational wave detection. But November 2018, LIGO had discovered like 11 gravitational waves. So, where do we go from here? By December 13, 2018, the scientific community at large, even the skeptical ones, had essentially agreed that, yes, LIGO did in fact detect gravitational waves and Gwen indeed existed. Jackson reportedly claimed that the Green and Moffat paper was absolute rubbish along with Nielsen's paper. However, Nielsen pointed out that LIGO is actually also at fault because the plots they used in their famous paper wasn't actually the result of the analysis they did for the detection in the first place. They were meant to be illustrative to help the reader understand what was going on. It is in the end on LIGO for not making this very clear. While Moffat and Green straight up claim that the Copenhagen team conspired to produce the correlation, Nielsen seems to take more of a moderate position, saying that LIGO should share part of the blame with regards to its data sharing practices. The Copenhagen team's last statement claims, "We have at no point challenged the existence of a signal in GW150914 distinct from the detector noise. Our concern is related to the physical interpretation of this signal as a gravitational wave from the merger of a black hole binary." Sure, but hold on, this is serious. This is how scientific consensus is formed, with a lot of fighting and a lot of passive-aggressive papers, except this time the fighting is a lot more public, so armchair physicists on all of your .coms argued about it, and Sabine Hossenfelder opined on it. The scientific method is not some clean, gentlemanly discussion over brunch. It's a street fight. And sometimes it's clear who's right and wrong, and sometimes it takes several years before anything of clarity even comes about. I would go so far as to argue that this level of skepticism is necessary, and honestly, the only part of the story that I don't like is how much of this raw process was exposed to the public, who are already having a hard time believing that scientists aren't some cabal engaged in a conspiracy to separate taxpayers from their tax money for no good reason. Yes, there is a difference between skepticism and conspiracy theorizing. Thanks, Hoss. Anyway, to wrap up this video and the drama, I guess, here is the most hilarious thing I read while researching this. To quote LIGO's spokesperson, "What of the controversy then? There is no drama here," Calogero said. "It's science as usual. Healthy, positive communication is very much welcome among scientists."